Hi, welcome to the fun probability problem solving sections. Today, we're going to work a very classical type of the probability problem. And so how to find the expected values here. So what is this problem tell you is if I have a random variables x, and so the random variable is a continuous random variable, have a CDF of a capital F of X. Then we want to prove it, the expected value of this random variable exists and can be represented as the CDFs here. Okay, all right, so like I said, this is kind of a very classical type of the probability problem. A lot of textbook, and they always have this type of the problem as for the proofs here. Okay, so now let's go to our whiteboard and let's take a look at how do we start it. Okay, so in order to work on this problem, I want to talk about a few common things we need to know here. All right, and so the first things here we need to know the few things. I use a different color here. This is the definition of the capital F of X, the CDFs, right? So, okay, so the first thing I think we all know, the capital F of X is equal to what? It's equal to the negative infinity to X. Then you just integrate the PDF ft dt. Be careful because here's the x, right? So your variable here is t. So because here's x, all right. Also, then we also need to know some calculus into the integration part here. So one of the first, this would be a simple integrations here. So if I integrate 0 to x dt. So I know this will give me what is t to what? X to the 0. So this will be x, right? So this is the type of the formula we're going to use here, all right? Okay, so now let's take a look. Let's start. Okay, so the expected value of x. Okay, so the expected value is, let's start with our fundamental definition about the expected value of x will just be the negative infinity is the whole domain, and the type the f of x, x times f of x dx, right? This is our traditional, the definition about the expected value of x here. And now, okay, so I'm going to use this trick here. I just did the x here. You can change to the 0 to the x dt's here. All right. Okay, so now let's okay, so this one here, I will change. This is negative infinity to the infinities, right? So remember this x, I can change to here. Okay, so I can change to, so this will be what? 0 to the x dt. Then I have f of x dx here. All right, so this is the first trick we're going to use in this integration. Okay, now the next thing here we can do is, because we can use this, we can break this, we can say this is from the negative infinity to 0, right? So this is 0x dt f of x dx plus, I just break this from negative infinity. So what I did here, I just break out this part, right? So this part, I can break out to 2 parts, right? So from the negative infinity to 0, or from 0 to the positive infinity. And then this is 0 to x. So the same things, nothing changed here. I say dt, then the f of x dx. here. Okay, so now the next things here, so this is just what I break these two here. So the next things here, I'm going to use one very important calculus technique here. I'm going to switch the order of integration variables. Okay, so in here, take a look here. I integrate dt first, right? I integrate dt first, then I integrate dx here, right? So now I want to switch that. Okay, so I want to switch to, the change to the dx first, then integrate the dt here. Okay, so now let's take a look at the first part here. The first part, this one here is mix negative infinity to 0, 0 to the x dt, and this is f of x dx here. Okay, so let's take a look at how do we, how do we change this ones here, all right? So for this ones here, so basically it's telling you t is from 0 to x, and then x is from the negative infinity to 0 here. So if you graph the domain of these integrations, right? So the x to t, right? So the t, remember the t is from 0 to x, right? So that means, okay. So this line here, I would say this is t to the what? To the x here. Let's put this axis is x, this axis, and I'm sorry, the t's here, right? This axis is t. So the integration regions here, take a look, be careful. So t is from 0 to x, but x is from infinity to 0. So the integration for this ones here is this area. Correct? Okay, so if the integration from here is this area here, so now I'm going to change, okay, so I'm going to change to the f of x dx dt. All right, so I'm going to change the dx dt. So because in this area, so now from the x directions here, right? So from the x directions, right? So the x is from, the x is from the t to what? So remember from this integration part, so from here, okay, so here from this integration part, that's here. From this integration part, I know the t is what? T is less than x here, right? Because the t is from the 0 to x here. Okay, so now I'm going to integrate from the x here. So the x where I'm integrating from t, right? So the t to x is where? To the negative what? Infinity. Then the dt, the t value is here, is from where to where? Negative infinity to 0, so here. All right, so now in here you can see the first part here. So this is the negative infinity to 0. And okay, and now I need to switch the order. Okay, I'm going to switch the order of this integration bound. So when I switch the order, what happens here? I have a negative sign here, right? So I have this negative sign. When I switch the order, is negative t. So the f of x, what, dx dt here. So this one's be negative. So what is these numbers here? So what is just these numbers here. This is what? This is our definition about what? F of what? This is our definition of f of t, right? From the CDF definition, this is f of the t. So then the whole things here, these things here will change to negative, infinity, to 0. Then this is negative, right? So if you, so what is here? This is f of t dt's here, right? So then we know that doesn't matter. So this is f of t dt's, right? Okay, now let's take a look at the second one here. The second one is the 0 to infinity. And then here, this is 0x dt f of x dx. Okay, so I do the switch the order again. So the first things I need to, right? So the here, let's see here, this part, right? So how do I switch the order? So when I switch the order, I'm going to do the f of x dx and dt's here. All right, so now let's take a look at what is this integration regions here, right? All right, so this one is the, so this is the t equal to x here, right? So this is x, this is t here. Okay, so first, so for t's here is from the 0 to x, but x here is from 0 to infinity. So what is the integration region here? Is oh, this one's here. I should this one's here. Okay, so this one here should cross the center. I just did not grab. Okay, so much better here, right? Okay, so for this ones here, so integration region for this part, what will be this part, correct? Okay, so this will be our integration region. So now when I do the t, you know, the integrator, so now if I do x here first, so what happens here? It will give me what? This will give me to the t, right? So it's the t, because the same thing, the x is greater than t, right? So it's a t, but now where? T to the infinity. Right, so this will give me t to the infinities here. And then, so now this is the t to the infinity. And then in here, I will have the 0 to the infinities here, correct? Okay, so now let's continue. Okay, so now from here, okay, so let's take a look here, right? You know, when we first start, we said this is the definition about the capital F of X, right? So we know the 1 minus F of X, what it will be, the 1 minus F of the X will be the X to the what? X to the infinities, right? Right, because we know that if you integrate from the negative infinity to positive infinity, will be 1. So this is the f of x. So then from x to infinity, 1 minus f of x. So this one here is from t to the infinity. So these terms here, okay, so these terms here, we can change to, so this will be changed to 0 to infinity, because this is t to the infinity. So what is this one going to change to? Will be changed to 1 minus f of t dt. Right? Okay, so now you combined. So now you combine both these two here. So these equations here, okay, so will be equals here, right? So this equation will be equal to, so the 0 to infinity, 1 minus f of the t, and dt, and minus negative infinity to 0, and this is ft dt. Okay, so even problem said it's x, because here the variable doesn't matter, so you can change this is just you said is 1 minus f of x dx, and minus, negative infinity to 0 f of x dx, right? So you can change it to d, you can change this t, doesn't matter. You can change this t, say, oh, how about this is w? That's fine. So you can say if this is dw's, right? So now we just change it to x. So let's match what is the problem it asks us to do. So, okay, so this is a pretty nice kind of the different way to find the expected values here. And the proof really just requires some very basic calculus integration skill. So the key things here is, how to switch the integration orders, right? You need to know how to switch the integration order and those basic definitions. And also, this is the one kind of a little tricky here. So you need to know how do you define the x is just like you take the integration 0 to x dt, then will give you x. So you just replace over the original one and then do a switched order. Okay, that's it. It's kind of a very nice proof, and I like how that turns out to be. All right, so the nice problem. Really hope you enjoyed it. Okay, talk to you on our next one. See you.